Right, my little friends, I hope we're all well, and welcome to Lecture 3, which is for software development for games. And this is classes and encapsulation revision. I hope you're all doing well during the pandemic. I've got a kicking lab for you today, so you'll probably quite enjoy it. It'll take quite some time to actually work through it, but we'll talk about that in a moment. So classes revision, you've been introduced to classes before, presumably, whether you're direct entry from college or whether you're actually continuing, and you've seen them in programming with objects before. So this should all be basic sort of revision for you to challenge you a little bit. So the purpose of this lecture is to re-look at classes in C#, particularly how to implement them. We'll talk about some object orientation concepts. We'll talk about UML, or the appreciation for the occasional need for a diagrammatic representation of ideas, which is sort of beneficial for game industry management positions, perhaps. I was talking to Paul Keir, who is a lecturer in the computer games technology program, and he used to work for Codeplay in Glasgow. And they said, he was telling me that at some stage there was always a board where some sort of diagrammatic representation of what they were attempting to implement actually went up in that board. So it was sometimes a UML diagram as well. So creates implementation clarity and appreciation of awareness and confidence. Or at least this is what this lecture and lab is really supposed to help with. Okay, so we could spend the entire trimester on UML for game design. We're not going to. There is a lecture later on, and I'll go through that. If you look at the gamesdev.net, you'll find some interesting opinions on UML. You'll see some people never use it, and some people swear by it, and it's very, very sort of contrasting. But after talking to Paul, eventually in a team of game developers, perhaps not on an individual basis, you'll need some form of diagrammatic representation just to make sure that you're all on the same page, presumably. So there are several ways of doing that. There's the unified modeling language, which we're going to stick with. There's the extended entity relationship model as well, from the days of yore, and more associated with databases and Shen. And then there's SSADM, which is structured systems analysis and design methodologies, which I think it possibly died a death, to be fair, but it is a sort of diagrammatic representation and can sort of help. They are arguably trying to sort of do the same things. You have your classes or your entities or whatever, and they all interrelate, and they have relationships between them. Some of these relationships can be recursive, or one-to-many, or one-to-one, or whatever. But they are sort of trying to model the same thing in a sort of formulaic, formalized, diagrammatical form. Okay. We're managing a team in 10 years, then this will be the time you will be getting the UML book out, apparently. So I'm told. So invariably someone in a games design team will start putting a diagrammatic sort of representation of what's happening on a board. So that's after me sort of talking to Paul. It's possible to generate class diagrams from Visual Studio. I've got 2017, it was possible way before that, but I've actually done this before in version 2017, or of course in 2019. So you can sort of reverse engineer a class diagram in the environment, so the IDE. And I'm not going to belabor the point about it. It's just to say that you can intrinsically see why these diagrams are sort of necessary and how they can be designed, implemented and sort of connected together. So what's the point of a UML class diagram? It gives us the ability to talk about a program at a sort of higher level of abstraction. So talking about the design rather than the implementation, because the purpose is to foster a sort of high level abstract discussion. Many details about classes can in fact be omitted from UML diagrams as well. but we will get into them at some stage. I believe it's lecture 6 or lecture 5. I'm not entirely sure. So the structure of this lecture today, we're going to look at object-oriented programming features, encapsulation, possibly abstraction, revision of creating new types and defining classes, revision of declaring data members and functions, instantiation of objects from those particular classes, setting the member access levels, and declaring static data members and member functions, and types of relationships in object-oriented programming. So what we're going to be looking at specifically there is composition and aggregation, and I've got an absolute kick-ass example of aggregation in the lab today, or the lab sheet, which I'm really quite happy about, I've got to say. I sort of came up with it out of my own design, and sometimes I just astound myself with my genius level intellect. So, object-oriented programming, a different way of thinking about programming. If you're not, it is the industry standard. If you don't know about object-oriented programming, then you won't get a job in the games industry or the software development industry, period. So, modern methodology used in the majority of games and software applications. And you can define differences in types of objects that have relationships with each other, and enabling interaction as well. So the key characteristics of object-oriented programming is that you can create your own types, and that's the magic of it, and create objects from those particular types. So it's sort of self-describing, not quite like metadata, but it is self-describing in the sense that you created. It is entirely your design, and therein lies the power of object orientation. So what are the key features of object-oriented programming? We've sort of had this before. The 4 pillars of object-oriented programming are, of course, encapsulation, inheritance, polymorphism, and abstraction. But there are other things in there, such as data hiding, overloading, and of course reusability is a big part. So encapsulation is really all about the sort of hiding, the scope, and compartmentalizing the functionality, okay, which we're going to be looking at specifically today. So these are the 4 pillars of object-oriented programming, and I do believe I've got that in your class test, so do remember that. The class test will be a multiple choice test this year, of course, online, and that's one of the questions in it. And of course, with multiple choice, everything is sort of coded in obfuscation. So just remember those 4 things, and what I mean by that is there'll be a number of red herrings in there as well. So abstraction, inheritance, polymorphism, and encapsulation. And I've put some other terms in there to sort of throw you off the scent, but just remember those 4, okay? So what is encapsulation? We're combining properties and methods related to the same entity or class. So it's trying to bind data and functions that manipulate data together. Okay, so it keeps it in a safe form and tries to sort of prevent misuse. So you do sort of think of it as a capsule. And there we have a sort of diagrammatic representation there of encapsulation. So think of a capsule, you think of the class, the methods, and the variables, all encapsulated, all in this particular capsule for use. Okay. So what is a class? An extensible program. It's really a template for creating objects. You're providing initial values, so you're putting it into, once you instantiate those objects, you're putting those objects into a valid state, as I sort of stated before in programming with objects. So you're putting the member variables into a valid state, and the implementation of behavior, member functions or methods are in there as well. So it's really a blueprint or a prototype from which the objects can be created. And they're user-defined data types and can be absolutely anything. So in C# your entire program, as you know, is obviously a class, okay? So in terms of defining new types, C# enables you to represent game entities as objects with member functions, data members, and whether these are, to sort of bring it into popular culture, you've got the Sith, the Jedi, the Orcs, the man flesh, hobbits, elves, weapons, ammunition, stars, planets, dinosaurs, angry birds, pigs, monkeys, plants, zombies, wizards, space, the list goes on, or even zombie mutant killer were-chickens. Okay, so here we have it. Little hobbit, there's Bilbo Baggins there, the Sith, the Jedi, who were massacred in Revenge of the Sith really quite quickly by Darth Sidious. Well, those three were, I really don't know why they showed up, but it was just to show his prowess with a lightsaber, I think, and then it was down to him and Samuel L. Jackson. Okay, we've got the elves, Thranduil there, my favourite elf actually. Sauron, although he is a particular class, he is like a boss. So even though you're saying orcs, it's not quite true there. And then of course you have multiple classes that can actually combine and interact in order to formulate the gameplay. So there you have, in Mario Kart, you have the character, you have the weapon, and you have the cart. Okay? Then of course you have animals like Epona from Zelda, that can be put into a class. Just to show you a sort of example of object-oriented programming and why it's useful and why it's reusable. There we have the castle from Super Mario 64, which was then instantly reused again in Super Mario Kart. So reusable code is really what we're sort of looking for here. Courses as well, or tracks. There's the Rainbow Road that we all love in Mario Kart, and that's all sort of contained within a class as well. And then of course you have Super Mario, that's Galaxy. As I said, I recently bought a Nintendo Switch. Oh no, where is it? It's Super Mario All Stars. It's somewhere, but Super Mario Odyssey there, and the Zelda games, and then the All Stars is actually Super Mario is All Star 3D. Yes, is Super Mario 64, Super Mario Sunshine, and of course Super Mario Galaxy as well. But when you're talking about classes, then of course you have your character, Mario, defined in a class, presumably, and then of course your different planets, galaxies, that sort of thing, all defined within a class. Then of course we have dragons. There are 3 dragons when Game of Thrones was popular. I was quite happy with the ending of Game of Thrones myself. I was very, very happy that the dragon massacred everyone and was unharmed. And the sort of main one survived, and you're going, excellent. So there they are there. You can say that a dragon is a particular class. You have Smaug there, which is a possible specialism, because he is the idea is through inheritance, you can then inherit all of that functionality quite easily, but then you do get specialisms that extend that functionality, and of course Smaug is an example of a specialism because he can in fact speak and is in fact quite intelligent. The Game of Thrones dragons are supposed to be intelligent as well, Viserion, Rhaegal and Drogon, but Smaug is particularly intelligent because he can in fact have conversations, and he's a bit of a psychopath. So he's quite excellent. So he's a specialism dragon. So there's what they sort of look like when they're a wee bit bigger. Mutants, there's my favourite mutant, Magneto, although I don't like that costume anymore. It's a bit much, to be honest. But mutants are a particular class. So if you think of Magneto, Professor X, Wolverine, they're all particular instantiations of that class, or objects of that class. Okay. So we have an example class definition in C++. This is just really for your information more than anything else, to sort of show you how to do this in C++. You of course got the access to Visual Studio 2019, so you can mess around with C++ if you see fit. And you can actually define these classes within C++. C# has a far nicer way of sort of doing it. So here we have a sort of class mutant in C++, so you define a new type mutant. You have the public sort of section, and then you've got data members. So you get mutant power level, underscore power level, which is just an int. Then you have some form of greeting, which is an example of a member function. And of course, you've got your semicolon there. Now, the part that makes C++ a little different is that you've actually got to go out with that class. So you have to go out with the class in order to sort of do the implementation of it, which can be quite handy depending on your style. But you've got to say void mutant and the sort of colon greeting in order to then implement that. Okay, so that's the member function definition there. And then you've got to use cout. I'm a mutant, my power level is whatever. And then of course the different sort of notation that comes with C++. Wouldn't really hurt for you to put that into the coding window, C++ coding window, of course, to see how to sort of work that. As you write this type, it can be anything that you like. It's easy to forget about this little semicolon, but the program won't compile without it if you do forget it. So do try that. It's not essential. It's just for your information, and to say that we've put a little bit of C++ into the course. And then in the main function, there we have it. It should be easy to sort of define two mutants. These are statically defined, not dynamically defined at this particular point in time. And you're using the dot operator to then set the power level. You're outputting the power level, and then you've got another mutant here where you've got the power level set to 4, and you're outputting the power level again. And then within the greeting, you've got access to that data member, and then you simply use the dot operator to access that particular functionality in greeting, and then that should give you the message, I am a mutant, my power level is this or that. And then in C++, you've actually got to pause the screen as well. So make sure that all of that goes in. Basically, just start up a simple C++ program, a console-based program in C++ if you want. Fire all of that in, and it should work. If it doesn't, it's not the end of the world. So if there's an object, is an instantiation of a class. So we're instantiating two instances of mutant. We're initializing the data members. The program won't actually compile if you don't initialize them and access them as well. And then you're accessing those data members as well, and calling the member functions as I've sort of indicated. So that's the C++ version, which of course we're doing C# in this module, but just to show you how lovely C# is in comparison. So there's a class mutant again. You have your public data member, which is M power level. Then you have your greeting. Notice that all of this is encapsulated within the class. There's no semicolon required here in order to separate it, and you don't have to then specify the class in the method definition later. So it's far nicer, a far nicer language to sort of get to grips with. And then all you're saying in the greeting is console.writeline, I'm a mutant and my power level is, yeah, and you're outputting the power level. Okay. So no semicolon after the bracket, so nothing to worry about, so that's absolutely lovely. And then of course you're dynamically coming up with these mutants again, and that is the exact equivalent of that program in C# as it was in C++. So you're statically creating these, and then you're assigning the power level, and then outputting the power level, okay, in each case, for mutant 1 and mutant 2, and then of course you're activating the greeting, so you're accessing the data member function, okay, and then you can of course pause that. Now once again, as in last week, when you look at the lab, it will ask you to do some of these things, but I haven't left you empty-handed. The code basically for the first one is there. So don't feel as if you have to write it off the top of your head. The entire idea is that you're always analysing the slides. You go through all the slides. Don't get C++ and C# mixed up, by the way, otherwise you'll be very, very confused. But you analyse the slides, you then try to practically implement it in the lab, okay? So it should be a fairly time-consuming process. You should be doing this for approximately 10 hours. At least that should be the amount of time that you should spend in independent study per module. And programming modules are particularly important, so make sure that you actually go through this meticulously and don't necessarily give up at the first sign of failure. I've had quite a few of the first years at the moment that want instantaneous results. They want to skim through everything as quickly as possible, get the code handed to them, and then compile it, and then that's it. It's just not the way to do it. You've got to meticulously go through all of these things, make sure that you understand them, and reproduce them, okay? So it's a time-consuming process, I know, but it's well worth the effort. Some of the first years were in fact hassling me for solutions. I denied them the solutions, and of course in your case, I mean, these things are in fact part of the assessment, but I denied them the solutions, and one of them actually wrote up today on the Aula system that it took about quite a long time. He's very, very satisfied with the results. So that's what I want for you people, and that's what programming is really all about. It's about the knowledge that the only thing that stands between you and solving a problem is time, and that's it, and that's all you need. You just need to take a breath and analyse these things in a formulaic, methodical way. And then, of course, you get the self-satisfaction and the endorphin rush when you actually manage to do something by yourself. If you just have the answers and everything handed to you, then it's very, very deflating. But I've given you lots of hints, and the answers to some of these things are interlaced within the slides, as they always are. So an object instantiation of a class, 2 instances of mutant. You're initializing the data members. Okay, I don't know if C# is quite as stringent as that. C++ will probably give you a rap over the knuckles, but I think that the program might still compile in C#. I'm not sure, you need to analyze that. You're accessing the data members, and then you're accessing or calling the member functions as well. So that should give you the exact same result. So that's to show you, really, I'm doing a sort of reason for comparison to show you that the selection of the language is really quite relevant, and it increases your confidence with data structures, algorithms and rudimentary programming, because that is what is really sort of important. The underlying transferable skills, selection of a language should be more or less quite irrelevant. Now, the reason I'm showing you that, Sherlock Holmes and Professor Moriarty, is that I was actually more or less mentored and trained by a professor, and I worked with him for many, many years. He was my supervisor for many, many years, and every time we were working on a project, I would always go into his office more or less sort of, you know, oh God, what implementation language is he going to pick out of the ether this time? But eventually it didn't become an issue anymore, because I could turn my hand to anything. And that's really what you have to do in this day and age. You have to be multi-adaptive. You've got to, even if you don't, make it look as if you have an insatiable appetite for learning, and see it as a fun, entertaining, rewarding challenge more than anything else. So you've got to get in about it, sort of thing. And that's the reason I'm sort of showing you that. So, constructors, there's going to be a question about constructors in your class test. There always sort of is. So these are special member functions. In the lab today, you'll experiment with making constructors as well. So in the class test, it actually does ask you, you know, what kind of state does a constructor create an object in, or something to that effect. And there are 4 answers. And one of them, of course, is a valid state. There's another one in a virtual state, in a void state, in terms of obfuscation. And you'd be very, very surprised how many people actually select the wrong thing. So it's in a valid state. We've had people ticking in a virtual state, and you go, not what I wanted. Okay, so they're called automatically every time a new object is instantiated in C# as well as C++. And there's a default constructor that has to be defined if you decide not to use the constructor that has been implemented with different parameters. So constructors, you can fire different parameters in to it, and the reason that actually the compiler knows the difference is because of the parameter types that you fire into the constructor. So that's another thing that's actually in your class test, so do remember that as well. So it's highly convenient. You're setting all of the member variables to a particular value. So here's an example constructor. This is actually a C++ constructor, so once again I apologize. You get your class mutant there, your power level, okay, void greeting, you need your semicolon, and for some reason everything comes out of the actual class and comes here. And what's happening there is when you call this constructor from here, okay, what happens, well, not quite from there, you're passing it in, that is the constructor prototype anyway, and then the power level is actually put in there as a parameter, as an integer, and then you're saying that a new mutant has been created, and this is a C++ program, so feel free to experiment with C++ if you want as well. That should take you another 7 hours, so put about 17 hours in this week, okay? Okay, so you get your void mutant greeting. I'm a mutant, my power level is this. And here we have it. The main procedure in the program is merely you creating a static mutant, you're firing in the integer 7, and then calling the greeting and system pause. Now, that will of course give you, I'm a mutant, my power level is 7, okay? This is the C# equivalent, as you can see it's far more convenient, so you get int power level, mutant power level, you get your greeting again, I'm a mutant, my power level is power level, okay? And then you can actually use this keyword to access the power level and make some form of difference between that. Now it's it makes you go cross-eyed when you have a power level that has to be set to the power level in the class being put in as a parameter. So that's the name of the power level that's going in as a parameter, but you've also got the power level up here that is in fact the data member. So how do you differentiate between the two? Well, there's two ways you can do it. You can either make that slightly different in terms of capital letters or whatever, or call it something different. You can call this MP level or whatever you want to do. But you can also use this keyword, and that gives you access to everything within that class, all the data members within that class. So you're going this dot and power level should pop up. Now, a good sort of way to make sure that your program is in fact working is to put in the sort of this keyword, hit the dot operator, and see if something actually appears. Now, if it's starting to recognize things, then the structure of your program is sort of okay. And if it doesn't start to recognize things, this is the same when you're actually as you know before from other courses you've taken. If you're hitting the dot operator and nothing is appearing, that's very, very suspect, and it doesn't look as if the program is structured together correctly. It's not recognizing it then. So it's a good sort of method of verification. So if you hit this dot, M power level should fire up there, okay? So there we go, you've got a static declaration of a mutant, so a new mutant object is being created and you're simply passing in 7, then you're accessing the greeting, fair enough, brilliant, okay? Then you can set member access levels. Objects, like functions, should be treated as sort of encapsulated entities. And basically what you're supposed to do is avoid altering or accessing object data members directly. This is considered to be bad. You can, it is your design, to make them all public if you want, but it's not really considered to be the sort of done thing. It's considered to be a bad design actually. Now, you can make them all public, it's entirely up to you. and you can access them from quite freely. But you set that access level, and it's really your design. But as long as you're aware of these options, then that's great. So you should be the data members or object member functions. The data member should be altered through the object member functions, and these are sometimes called mutator functions or set or get. And set always takes parameters generally, and get returns values. Now there is a set and get question in your class test as well. We will go through the class test in a great deal of detail, but just so that you're sort of aware of it. So this is a C++ member access level example. Now, as you can see, we also have, instead of just public now, we also have a private section, okay? In C#, you can more or less define these things all independently, and it's quite nice. But in C++, you have a public section and you have a private section, just to be difficult, okay? So in the private section, you now have the mutant power level, where before it was in the public section, right? So what sort of happens there is you've got to then use the constructor, in this case, to then access the power level and take the power level in, okay? So a new mutant has been created, and it will only be recognizable within that class. If you try to access it out with that, you wouldn't be able to see it, okay? So this is now private, okay? So you've got int mutant get power level, and it's returning, yes, so that's the get equivalent of C++. So really, you should notice, regardless of programming language, that an integer is returned here, and you're returning the power level, which is an integer. And then, of course, you're setting the power level in this set mutator function. So it's you're bringing in the power level as a parameter, and then you're putting in a little bit of error checking as well. And if power level is less than 0, you can say that the power level can't be negative, else you're just setting the power level to the power level. Now, what I've sort of done there, you'll notice that this is slightly different because M power level, and you're just putting in power level. Okay, so mutator functions, accessor, member functions, okay? And that's how you actually call it in the main. So once again, if you're wanting to start up a C++ program, fire all of this in, it should more or less work. So you've got your static declaration of an object there. You're firing in the parameter 9, and you're calling get the power level, okay? You're then setting the power level to -1. It'll fire an error back at you and it'll say it can't be negative. Then you're setting it to power level 7, and it'll say everything's hunky-dory. And then you're outputting that particular power level. So that's example member access at level. So you notice that the get power level is a constant member function, so it can't change the value of any non-static data member, okay, declared in the class. And it can't call any non-constant mutant member function, and it only returns the value and doesn't modify any data member as well. So that's just a little bit of information for you. This is the same sort of thing in C#. Now, I'm asking you to do this today in the lab in C#, so I'm not leaving you empty-handed. Everything is sort of here anyway, okay? So you've got your power level, and you can see that each data member, each function then has private, so that's now set to private, whereas C++ is different, it has sections, so that's now independently set to private. You then have public greeting, that's the constructor here, okay? You're setting this dot power level to the power level that you pass in, and then you're actually you've got a sort of set and get. Now these are in fact properties, which is a rather convenient way of doing the sort of set and get functions in mutator functions in C#. So do look at these. It's a lot to take in. And don't worry if you don't get it immediately. This should be a sort of slow process. So this is now private, okay? You get your mutant and your accessor. That's really a property now. And that is far, far simpler. So if you fire that into the coding window in a C# program, console program, then everything should be fine. So you get mutant, your mutant 1, you're creating that statically, you're firing in the parameter 9, you're then outputting that. Remember that you can in fact use this little $ in C# in order to access these particular data members, okay? So if you put the $ in, you can then encapsulate all of that in nice little inverted commas. But using the curly brackets, you can then isolate the data members that you're wanting to output to the screen, which is a very, very sort of nice, handy piece of functionality, which is really just for your own information and to make your program a little bit tidier, a little bit more convenient. So do try to remember that. If you want, again, it's entirely for your own design, but do analyze these things. So mutant level, mutant1.power level is equal to 1, and then you're calling the greeting, and that's fine. So static data members and member functions. So each instance of an object stores its own set of data, meaning unique identity. But you can, however, store information about an entire class. So that's what we mean by static data members and static member functions. And this could be, for example, the total number of instances that exist. An example of this that is applicable to games, if you have created a group of enemies and you want to fight the player based on number, and storing the total number of instances in each object would in fact be a complete and utter waste of time, and it takes up space and it's relatively cumbersome. And the best way to access this kind of variable is through a static data member function as well. So I'll show you how to create these. In C++, maybe we should possibly avoid this confusion, but it is here anyway. I've got a class dragon, you've got your sort of public thing here, then you've got your static total, okay? That's the static data member, and this is the static data member function. Okay, so you're able to access that through the entire class. So static data member, the total number of dragons in existence, okay? That's fine. So here we have what you would put into the main, okay? Now notice that as I create them, that the static data member is increased or incremented. So you get S total, there it is there, and every time you create one of these through the constructor, then you increment that. Now as I say, C++, just there for your information, so don't worry if you don't quite get this. So total number of dragons is, okay, and then you're accessing the static data member function through C++, creating 2 new lines, you're creating 3 new dragons, let's call them Drogon, Viserion and Rhaegal, and then the total number of dragons, then you're getting the total again, okay? So that means that if you actually put that into the coding window properly, it will give you the total amount of dragons in existence, okay? You've also got to, outside of the class definition in C++, you've got to qualify a static data member within its sort of class name, sorry, with its class name. Okay, so outside the class, you've got to use that with its class name here in C++. It's a bit of a swine. And you can access the data members and static member function outside of the class by qualifying them with the class name, and that's how you do it. Okay? So, it's possible to declare static data members in non-class functions as well, and it will maintain its value between calls. So that's something to sort of bear in mind. So static data members and member functions in C#, static variables have the same value for all instances. So if instance 2 changes the value, then instance 4 will see it. So if instance 2 changes the value, instance 4 will see it. And these can be useful for keeping track of objects. Okay, static methods. This means that you don't need to have an instance of a class to call it. Okay. So here's an example here. You've got your sort of class mutant again. you've got your public static int mutants existing. You've set that equal to 0, okay? And then every time you create a new mutant, okay, this is in C# and this is all in the lab today. So once again, look at this particular piece of code when you're talking about static data members and member functions. You're instantiating that to 0, and every time you call the constructor, which is mutant, you're then incrementing the mutants existing, so that particular variable there, okay? Now, when you then put this in, you're creating 4 mutants. That will increment all of that, and then you can then access the static data member by prefixing it with the class name anywhere. So console.writeLine, and you're saying mutant.mutants existing, yes, and that will come up with there are 4, okay? So you can access static data members and static member functions outside of the class. You've got to qualify them with the class name. So there's examples in that today. In one of the books that I sort of taught in over the years, and this is just an example, in chapter 8, there was a sort of critter caretaker game, and here we sort of have a class definition for that. So it was a sort of pet thing, a sort of pet game. I created it into critters. Where are the rights? And we have hunger, boredom as integers, and then of course you've got your, this is just an example of UML, so you've got your class name here, you've got your data members here, and then you've got your methods here, your member functions, which is talk, eat, play, and pastime. Now obviously these variables interact with these and then result in the sort of interaction gameplay. So get mood, calculated based on the hunger and the boredom. Pastime is private. It's only called by other member functions as well. So there's a bit of pseudocode associated with that. This is just again for your interest. While the player does not quit the game, you present a menu of choices and you can keep this sort of going. If the player wants to listen to the critter, you make it talk or say something. If they want to feed it, you make it eat and alter all of these variables. And if the player wants to play, you make it play. Okay. So there are types of relationships in object-oriented programming. It should be clear by now that one of the greatest advantages is in fact code reuse. Yes. And there are generally sort of code reuse is possible due to the relationships between and within the classes. And there are generally 4 types that can be modeled in the UML class diagram. And these can be implemented into a programming language. So we'll get inheritance. There's going to be more in that next week. We have association, composition, and aggregation. So typically developers keep all of their classes in their own files, so that's a sort of structure to do. You'll learn how to do that in the lab today. Once again, I know it's asking a lot of you, but this is more or less the assessment. So you're working towards the assessment as well. So do remember that. It's not a complete and utter, frivolous exercise. Typically, and what I'm going to do is I'll put submission links for each lab. I'll either do that today or at some stage. It's a cumbersome exercise. They will appear at some point. Keep all of your labs, and then we'll use that for the purposes of getting you marks at the end of it. I haven't decided how I'm going to quite work that this year. So typically developers keep all of their classes in their own files, so each class per file, basically each file per class. And a class can have references to other classes and members. So types of relationship and object association, this is a HAZA type of relationship, and this can be one-to-one, one-to-many, many-to-many. Now this is your design, this is how you see things. Now I've taken the game of 10-pin bowling. In 10-pin bowling you have a score, you have a roll as well, and the amount of pins goes in there is a parameter. So the game, 10-pin bowling, of course, has 10 frames, so that's an association, yes. A frame can can have 1 to 2 rows of the ball, except for the 10th frame, which is a specialization which can then be inherited from frame. And you can actually have 1 extra row in the 10th frame, if you remember correctly. Okay, so it's an example. This is my design. Okay. So aggregation, this is a different sort of specialization. So we've had association. A whole is formed by combining several separate elements. Now, in the lab today, it's a wonderful example. We have a sort of car exercise, car aggregation exercise, and you've got to put in all the details of a car, or many cars, and then the details of their particular engines as well, and say that a car, in fact, is comprised of an engine, as it would be. Yeah, so comprised, combining several separate elements. So a material or structure formed from a mass of fragments or particles loosely compacted together. So that is another definition of aggregation, but we won't go into that. So here's an example. Sometimes you want to model a whole part relationship where one class represents the larger thing, the whole, and one class the smaller thing, the part. So let's have a look at this. A school, yeah, one school will have many departments. That's an asterisk there. Absolutely fine. Or can have many departments. Yeah, depends on what you're wanting to model. Yeah. But of course, you have another sort of thing. Here's a car here, and generally a car will have 1 engine, unless possibly specialised cases. A plane, for example, will have 4 engines, maybe, depending on purpose. Okay. And of course, in a plane, safety requirements are things, so you're not wanting all the engines to cut out at once. So, one car will have 1 engine, and 1 engine belongs to only 1 car. You can't have an engine belonging to more than 1 car. Okay, so that's the way it sort of goes. So here's a better sort of more popular example. You get Thanos, big Thanos there. And Thanos, the Infinity Gauntlet really belongs to Thanos, or at least it would, unless you consider when Tony Stark connected. But forget that. So, really belongs to Thanos, was made for Thanos, and the Infinity Gauntlet has 1 owner, or only 1 person can be wearing it at a time. But the Infinity Gauntlet also has 6 Infinity Stones. So reality, space, the power of the time, and the Mind Stone, yes. So that's how that's sort of modelled. So 6 Infinity Stones fit into 1 Infinity Gauntlet, yes? And 1 Infinity Gauntlet can have 6 Infinity Stones, at least in that model. Right, here's another sort of example. If you're going to Lord of the Rings, you get big Sauron there. He's got his ring of power. And of course, 3 rings were gifted to the race of the elves, 7 to the dwarf lords, and 9 were gifted to the race of men who above all else desire power. It was one of 9. It's a name which is long forgotten. Anyway, the point is that the 1 ring can only really be wielded by Sauron, okay? There's only 1 Lord of the Rings and he does not share power. So there we go. I think it's lovely, beautifully illustrated. So 1 ring belongs to Sauron, okay? And then the 1 ring can in fact be used to power, not power, not really the word I'm looking for, command, that's the word. Command the rest of the rings. So the 1 ring can command the 3 rings from the elves, the 7 rings from the dwarfs, and the 9 rings from men, okay? So it depends, it's really your design. Aggregation, you've got Darth Sidious there. He has his weapons. For some bizarre reason in the Clone Wars, he has 2 lightsabers. These lightsabers just come from nowhere. He also has his entire empire. He's quite rich, actually, let's face facts. He's got quite a lot of real estate. Exegol as well in the sort of final movie. He's got his Death Star, he's got his entire empire. That's quite good. He's also got his apprentices, and even though that's supposed to be on a sort of 1-to-1 basis, He has Count Dooku, he has Darth Maul, and then of course he has Darth Vader, and he has his force powers. So this is an aggregation example as well. So he's got lightning, he can throw things. He's also able to heal people. He can do his sort of force push. Why is that there? I think, well, yes, it's because he can actually project into the future. Everything is proceeding as I have foreseen. Yes, my young apprentice. So he's got all those powers as well. So that's a sort of example of an aggregation. And here's a sort of an example of an aggregation as well. When you're considering Black Ops, you've got a class with a primary weapon, a secondary weapon. You can have 6 perks. Lethal equipment as well, so that's a sort of Black Ops 3 example. You can also have containment, so try to remember that sometimes it's near impossible to model the clear associations, and these are just sort of small trivial examples to get you sort of thinking about it. And you can even have classes within classes, and that's actually called containment. Okay. Composition, so you get aggregation, you get composition, where one class owns an object from another class. So what is the difference? Okay, so the aggregation, the child class can exist independently of the parent, and in composition, if the parent dies, then the child in fact dies. So that's like in Underworld, where you've got Marcus there, who's apparently the leader or the father of all the vampires. He sired all the vampires, and he more or less says that if you kill me, they all die. And in some sort of vampire permutations, that is in fact true. Kill the head vampire, and everyone else either dies or returns to normal. So that's a sort of composition example. And in game mechanics, you sort of have that mechanic called permadeath, where the mechanic means that the character permanently dies. And many sort of arcade games have it. Super Mario Land, you permanently die. There's 12 levels, and you get put straight back to the beginning. Pac-Man, permanent death again. Batman Returns and the Super Nintendo, permanent death. Space Invaders, permanent death. R-Type, permanent death. And you get these sort of game mechanics in roguelike games, which is a sort of subgenre of RPGs. You get sort of permanent death of the player, and sometimes in survival horror games as well. It's just to sort of give you an idea of genre as well. So Don't Starve, and this is Granny, which my nephew was obsessed with at one stage. He wanted Granny to kill him all the time. Anyway, you've got these examples here, and if Granny whacks you, then you're permanently in and have to start the game all over again. And that was actually implemented in Unity 5. So in MMORPGs, because of what players actually desire, the concept of permanent death is not really particularly popular, because you spend your life amassing objects in these games, and then the idea of permanent death, everything, all your worldly possessions or virtual worldly possessions are then gone. So end of slideshow there, and just to sort of talk about the lab slightly today. Let's see. So the lab today, work through it, is how to define a class, how to declare data members within a class, how to instantiate objects, define data member functions within that class. So we'll show you how to define that class, a simple program using classes. So this is the sort of mutant example. This is it all broken down into pseudocode. So use the slides as well. This is basic pseudocode. If you cannot follow this, make sure you follow it meticulously, okay? And every little step is there, okay? I've probably left very, very little out. The answers are more or less in the slides anyway, so don't just skim this, fire everything in, and then expect it to work, and then go, I can't do it. You've got to meticulously go through everything, okay? So this is a simple program using classes, fair enough. Then you get a nice exercise 2, a program demonstrating constructors, which is quite nice. So you can do that. And then exercise the program demonstrating member access levels. So things get a little bit different as well. Exercise 4, static data members and functions, relatively easy. And then I've got this advanced exercise, which is basically creating an array of 100 mutant objects, calling the constructor and using a random number generator to generate the mutant power level. Use a for loop to populate the array using the array.length function to control the population for the loop. Fabulous. And after this is done, use another for loop to print it, all of the greetings for the mutants. And remember that you have all the internet resources. I'll maybe use this, if people manage to get this done sort of effectively, I'll maybe use this as part of the assessment, but to a greater extent. I'll maybe give people 10% perhaps, or 5 to 10%, if they can manage to sort of get that working. So I'm not going to shower you with the answers for this. There was a guy in the lab last year that took absolutely ages to get this working. It's designed to drive you crazy and designed to give you a challenge. And I'm not, please don't contact me and say, Thomas, I want the solutions for this, because I'm not giving them. You're not getting them. It's not as if some magical genie is going to come along and give you the answers to everything anyway. So do sort of get used to that. And it is sort of an assessment as well. So that's really a bit of a learning curve. So do try it. It's brilliant. You'll like it. And then once you get it, you'll be very, very chuffed with yourself. The next one is creating other classes. You can sort of do that as well. Don't really fixate too much on that. I've said create a circle, rectangle, triangle. In each of these classes, you should add methods to calculate the area and the perimeter. How easy is that? Then I've got this fabulous aggregation implementation class example at the end. And it's a very simple example of aggregation, and if you just follow everything sort of carefully, everything will be hunky-dory. So you've got a number of cars, and each of these cars will of course have an engine. And what you're doing is you're printing out, eventually you're populating all of this, and you're printing out, you're creating the different files for the different classes, and then you're printing out the class, sort of the car, and of course the engine. So a lot of work to do this week. It's probably one of the more evil labs, to be honest, but it is well worth it. As I say, the advanced exercise is designed to drive you a bit crazy and to separate the men from the boys a bit. As I say, I'm not really planning on giving a solution to that. I quite like seeing people trying to get it in the labs, and okay, I've maybe given little hints in the past, but once they sort of get it, it's almost as if they're on top of the world, so it's all totally worth it. But as I say, it's designed to drive you a bit nuts. And if you can't eventually get it, then fair enough. But please don't send me emails saying, Thomas, please give us the solutions. Not going to happen, because I can already do it all. I'm fine. I can get a job programming, no problem. Tomorrow, no, I wouldn't. I'd be chain smoking, thinking, oh God, I'm going to lose the company. But anyway, that's basically what it is. And you'll enjoy doing it, but it will take a little bit of time. So take about 8 to 10 hours this week to meticulously go through all of that. As I say, it is sort of part of your assessment. This will contribute to your assessment. I'll put submission links on the My UWS site, and this is you sort of working towards it. So let's say that this time is a sort of continuous mode of assessment rather than just something sort of summative at the end. Okay, right, so if anybody's got any real problems, then give me a call or whatever. Okay, have a good day, my little friends.